A finance employee gets a video call. The CEO is on screen, so are 6 colleagues. They discuss an urgent confidential acquisition. The employee wires $25 million. Every person on that call except the employee was an AI-generated fake. This is deepfake phishing, and it is happening right now. In this video, we are going to break down exactly how deepfake phishing attacks are constructed. We will look at voice cloning, how attackers generate a convincing audio clone from a 3-second sample. We will cover video deepfakes, how fake video calls are built, and why they fool trained professionals. We will go through AI-generated phishing emails, the personalization pipeline that makes them indistinguishable from real messages. Then we will get into detection, what signals give these attacks away, and what organizational defenses actually stop them. This is intermediate content. We are going past the headlines and into the actual mechanics. Every deepfake phishing attack follows the same 5-stage structure. Understanding this structure is what makes defense possible. Stage 1 is reconnaissance. Attackers identify the target organization and specific individuals. They need 3 things: a high-value target to impersonate, typically a CEO, CFO, or executive with financial authority; a high-value victim, typically someone in finance or IT with the ability to move money or access systems; and raw material, audio and video samples of the person being impersonated, scraped from earnings calls, conference recordings, LinkedIn videos, and press coverage. Stage 2 is cloning. The audio sample is processed by a voice synthesis model. The video, if needed, uses a face swap or full avatar generation pipeline. Attackers use commercially available tools, many of which have inadequate safeguards. Stage 3 is crafting the attack payload. The cloned voice gets a script. The email gets personalized using LinkedIn data, company press releases, and internal project names scraped from job postings. The more context the attacker has, the more convincing the payload. Stage 4 is delivery, a phone call, a video conference invite, or a targeted email to the right inbox. Stage 5 is exploitation. The victim takes the action: wire transfer, password reset, credential handover. The window between delivery and exploitation is often under 10 minutes. Voice cloning has crossed a threshold that most people do not appreciate. 2 years ago, a convincing voice clone required hours of training data. Today, the state-of-the-art requires 3 to 10 seconds of clean audio. Here is how it works technically. The model is given a short reference audio clip, the target's voice. It uses a speaker encoder to extract a voice embedding, a mathematical representation of the speaker's voice characteristics, pitch distribution, format patterns, speaking rate, prosody. That embedding is fed to a text-to-speech synthesizer, which generates new speech in the target's voice from any text input. Commercial implementations can produce results indistinguishable to untrained listeners from a sample as short as 1 minute. Attackers do not need a minute. They need a public earnings call, a LinkedIn video, or a conference recording. Those are all publicly available for virtually every public company executive. The resulting audio is not perfect. There are artifacts, unnatural pauses, slight pitch inconsistencies, occasional clipping at consonants. But in the context of a phone call with background noise or a video conference with audio compression, those artifacts are masked. Human brains are not calibrated to detect subtle audio artifacts when the emotional context, urgency, authority, familiarity is present. Phishing calls use urgency. This is confidential. Do not discuss this with anyone. We need this done in the next 30 minutes. Urgency suppresses critical thinking. The technical quality does not have to be perfect. It only has to be good enough that the victim does not stop to question it. The Hong Kong case, the $25 million loss, used a multi-participant video call where every participant except one was an AI-generated fake. How is that actually built? There are 2 main approaches. The first is face swap. taking a real video of the target and replacing their face in real time or in pre-recorded footage with a synthesized version. Tools like Deepfake Lab and commercial APIs make this accessible. The quality depends on the quality of the source footage and the computing resources available. The second approach, increasingly common for full meeting scenarios, is avatar generation, generating a fully synthetic video avatar that mimics the target's appearance, voice, and mannerisms from reference footage. For a fake video call, the attacker has several options. Pre-recorded. A fake video plays in the call while the voice is real-time cloned audio. Real-time. Emerging tools can apply face swap filters live during a call. The telltale signs of a deepfake video call: lighting that does not match the environment, hair and edge artifacts around the face, unnatural eye movement and blink patterns, slight audio-video sync delays, backgrounds that look too clean or slightly unstable. These artifacts are visible when you know what to look for, but in the context of a pressured business call, very few people are actively looking. The third vector, AI-generated phishing email, is the highest volume attack because it scales. A single attacker can send thousands of hyper-personalized emails per day. Here is the data pipeline attackers use. First, they scrape the target organization. LinkedIn gives them employee names, titles, reporting structures. Company websites give them project names and division structures. Press releases give them terminology and recent announcements. GitHub gives them tech stack details. Job postings are particularly valuable. They reveal internal tools, platforms, and priorities. Second, they identify a target individual and a plausible sender, typically a colleague 2 levels up, an IT help desk address, or an external partner. Third, they craft the email using a large language model with the context injected as a system prompt. The model writes the email in a style consistent with the organization's communications, references real projects or announcements, and uses the correct internal terminology. The output passes every traditional filter: no malicious links in the initial send, correct grammar, no generic greetings, no urgency flags in the subject line. The urgency is in the body, written to feel like a completely normal internal communication about a time-sensitive matter. Traditional anti-phishing training fails against this category of attack because it teaches people to look for signals that are simply not present. The most sophisticated attacks combine all 3 vectors in sequence, and the timeline is faster than most organizations can respond. The attack chain starts with an AI-personalized email from what appears to be the CFO's office. It references a real acquisition the company announced last quarter. It says a confidential call has been scheduled to discuss the financing structure. The victim receives a calendar invite for a video call. The video call includes the CEO and 2 advisors, all deepfakes. They discuss the acquisition in credible detail, using correct terminology and referencing real internal projects. At the end of the call, the victim is asked to authorize an urgent wire transfer through a new banking intermediary, confidentially, before the public announcement. The victim hangs up. Within minutes, their personal cell phone rings. It is the CEO, voice cloned, following up to confirm the wire. This multi-channel confirmation exploits the psychological tendency to trust a message more when it arrives through multiple channels independently. From first email to completed wire transfer, under 4 hours. Most corporate fraud detection systems have alert thresholds measured in business days. Detection of voice deepfakes works at 2 levels: technical analysis and behavioral signals. Technical detection uses audio classifiers trained to identify the artifacts of neural text-to-speech synthesis. Real human voices have microvariations in pitch, timing, and intensity that are extremely difficult for synthesis models to replicate exactly. Deepfake audio tends to be slightly too consistent, the timing is too regular, the pitch variance too smooth. Spectral analysis reveals frequency artifacts at the boundaries between phonemes that differ from natural speech. Open-source tools like Resemble Detect and commercial offerings from enterprise telephony platforms provide deepfake audio detection. The behavioral signal approach does not rely on audio quality at all. Instead, it uses out-of-band verification. Any request involving financial authorization or credential change requires confirmation through a pre-established channel. Not callback to the number that called you, not the email address in the request, but a separate channel established before the interaction began. This is the one defense that AI deepfakes cannot defeat because it requires access to the victim's actual secure communication channel. Video deepfake detection focuses on artifacts that current generation models consistently produce. Temporal inconsistency is the most reliable signal. Real human faces have micro-movements, sub-pixel variations in position, subtle muscle contractions, involuntary micro-expressions that are very difficult for synthesis models to reproduce consistently frame to frame. Detection systems use optical flow analysis to identify faces that move with unnatural smoothness or that have inconsistent motion between facial regions. Blinking is a reliable tell. Deepfake models trained primarily on images where subjects have their eyes open tend to produce unnatural blink patterns, blinks that are too infrequent, too fast, or that show slight frame artifacts at the moment of closure. Physiological signals offer a more robust detection path. Real faces show subtle color variation from blood flow, a signal called RPPG, remote photoplethysmography. Deepfake faces do not reproduce this signal accurately. Lighting coherence is another signal. Real-time deepfakes often fail to match the environmental lighting to the face with perfect consistency. The challenge? Detection accuracy is in an arms race with generation quality. As models improve, artifacts diminish. The best organizational posture is not relying on detection alone. It requires procedural verification. Four organizational defenses have measurable impact against deepfake phishing. First, out-of-band verification for all high-risk actions. Any request to transfer funds, change banking details, grant system access, or reset credentials requires verification through a pre-established channel, not the channel the request arrived on. This single control defeats the most sophisticated deepfake attacks because the attacker cannot fake the verification channel. Second, technical controls at the email and telephony layer. AI-powered email security that analyzes sender behavior patterns and content signals catches AI-generated phishing that passes traditional filters. Real-time deepfake detection in video conferencing is emerging. Third, updated security training. The Signal's employees are trained to look for typos, generic greetings, suspicious links do not appear in AI-generated attacks. Training must shift to behavioral. Any request that bypasses normal authorization processes is a red flag, regardless of how legitimate the communication appears. Fourth, a response protocol for suspected deepfake attacks. Employees need a clear path to pause and verify without fear of embarrassing a genuine executive. The protocol, I will confirm this through our standard verification channel before proceeding, is a complete, acceptable response to any request, no matter who appears to be making it. Quick recap. Voice cloning requires 3 seconds of audio and produces convincing results at scale. Video deepfakes can fake entire meeting participants and are increasingly used for high-value fraud. AI-personalized phishing emails defeat traditional training and filters. Detection exists, but is in an arms race with generation. Procedural defenses are more reliable than technical detection alone. The one control that defeats all 3 attack vectors, out-of-band verification for any high-risk action. Make it a reflex, not an exception. If this breakdown helped you understand how deepfake attacks are actually built, subscribe. We cover AI, security, and engineering every week. The companion article with specific detection tools and implementation guides is in the description. Next week, Zero Trust Architecture Deep Dive, beyond the buzzword and into the implementation. See you then.